Yeah, so let's just go ahead and get into this because I think Will covered all of my introductory stuff. The first question is why do this? And I think for this audience, like maybe I don't really have to answer that. I think a lot of us like just, well, like of course, why wouldn't you do it? But like my first reason, like it's fun. Like Will mentioned this, I've written a whole bunch of compilers in Scheme before, and I like to do this. And so you know, I was working on WebAssembly, and I was like, let's write more compilers. But I think there's like more than just my own like gratification. There's reasons to do this beyond just you know, writing code that's cool. So one is WebAssembly is, and I'll do like an introduction to WebAssembly later. So if you don't know what that is, that's okay. But so WebAssembly is meant to be a target for a wide variety of different programming languages. Like you want to be able to compile the WebAssembly and have it run fast in the browser. And so one way to prove this is to implement other languages on WebAssembly. And then the other thing is that WebAssembly, you know, it has a pretty good set of features now, but there are some features that would be great to add to it so that we could better support more languages. And so I thought it would be great if we could have a language implementation, in particular that's small, so that we can try out new features quickly and see, and basically get implementation feedback. So we make sure that we don't design something for WebAssembly that turns out to just be like, you know, oh, it looks good in theory, but it's really hard to apply in practice. So that's kind of what got me started down this path. So let's talk about WebAssembly. If you go to the WebAssembly website, you will see this. It says WebAssembly, or WASM, is a new portable size and load time efficient format suitable for compilation on the web, or to the web, I guess. So this is, if any of you are familiar with ASM.js, WebAssembly is sort of like if ASM.js grew up, this is what you would end up with. So it draws from a lot of those same ideas, but it's this portable bytecode format that you can compile code down to, and then load it very quickly. It's very compact, so you can download it quickly off the web. You can compile it to native code quickly, and then your code that you actually produce will also be fast. And so you can run basically native-like applications from your web browser. So I'm going to go into a little more about the features there, because I imagine a lot of us in this room are not like familiar with the guts of WebAssembly. I don't have time to go like really into depth, but I'll try to highlight some of the important parts. So maybe for this room, the most important thing, or actually, this is coming up later. So how WebAssembly works. You start out with your C++ source program, and then you use like a toolchain, or C++ or any other language. Like C++ is the one that we support the best now. You use your toolchain, so Emscripten is the like batteries included C++ and C to WebAssembly compiler. And then you compile your program, and then it can run in the browser. And so you can get these really cool, rich applications, basically using existing code, because we support C++ really well. Okay? So I think this is the part. No, not yet. Okay. So here's a more in-depth example of, you can write some code in C, or C++, I guess. This is C. Then you compile it, and then you can run it in a web server, and then there's our hello world. So it is just plain old C, and it works in the browser, and it's like magic. Okay? So the WebAssembly language. For this room, the really cool thing about it is that it's S expressions. It has. Okay, so WebAssembly got S expressions for at least for its text format. There's a binary format that's what you actually put up on your website. It got S expressions basically the same way that every other language I know of that has S expressions got them, which is no one could agree on a syntax, and we didn't want to write a parser. And so I think, as I understand it, one day Andreas Rosberg was like, I'm going to write an S expression parser, and then everyone's like, okay, cool, we'll stick with this, like this works. So Andreas is maybe a part of the reason why I'm here today. So, but WebAssembly is also a stack machine, and so that's kind of weird to represent that way. So I want to introduce this thing we have, the way that S expressions can fold, and I'm mostly pointing this out just so that you can understand some of the, so if this shows up later in the talk, it will not seem so unfamiliar to you. So here's just sort of the completely unfolded version. This is, it pushes two constants onto the stack and then adds them together. But you can rewrite this by folding them inside to make it look more like S expressions. So this expression here is equivalent, where we folded the const 10 arg into, or like instruction into the add instruction. This is probably not really where you would want to stop. What you really want to write is this. So that looks much more like you would expect in an S expression language, but all three of those forms are actually equivalent. Okay, that's just an introduction to the syntax for later on. I mentioned it's a stack machine, so here's an example of how that's the actual like bytes that you would put on the wire to encode that math expression. So you push 1, 2, and 3 up on the stack, you multiply 2 and 3, and then you add 1 to it, and then so it respects order of operations and all that. There are also, in addition to the stack, there's local variables. So you can declare these locals that have different types. You can use getLocal and setLocal. And in a lot of ways, they work just like registers. And in fact, the LLVM backend for WebAssembly basically just treats them as registers and doesn't really do a lot with the stack. It uses WebAssembly as a register machine in general. And WebAssembly is statically typed, but it's kind of a very, it's like the simplest type system you can make and call it statically typed. So there's 4 types in it. There's I32, I64, so 32 and 64-bit integers, and then 32 and 64-bit floating point numbers. And then basically everything else is just making sure that we use those the way that you say you use them. There are proposals in flight to add much richer types to this, which will again help support more language features on top of that. And then in case registers and the stack is not enough for you, which it probably is not if you're doing like any kind of like real large program, there's a linear memory in there. And so you access it with load and store instructions like I have there. And it's basically just like offsets into this big linear array. And then if you're in the browser, you can access this as an array buffer also. And that's when we can do data interchange back and forth between the two of them. Okay, cool. And then finally, it has structured control flow, which this is where WebAssembly as a assembly language starts to kind of break down. It's not really an assembly language because assembly is usually go-to and jumping to like different like bytes of memory. And so, but the structured control flow lets us have, basically it makes it easier to get the typing. You can use a pretty straightforward type checking algorithm for it instead of having to do anything really like esoteric. And then makes it easier to do control flow integrity and all of those properties that we would like, given that one thing WebAssembly lets you do is run untrusted code from the internet, which as hopefully we all know is a very dangerous place, and kind of keep it contained and safe. Here's an example of a loop instruction in WebAssembly. So it's basically this is an infinite loop actually. So you get down to, you go in the loop, you call a function foo, BR0 says, okay, break up to the last label, which is the top of the loop. And then it just does that again. So actually this call bar never gets executed in this case. It's just an infinite loop. In Scheme, it's the same as let loop, and when you call before you actually get all the way down there. I did a version of these slides once where I used C as the example because I was speaking to more of a C audience, and this was much harder to write in C, actually. So WebAssembly's control flow, at least these like basic things, map really well onto what Scheme gives you, although not so well with call CC, as maybe we'll see later. And then here's if. So you if there's a instruction, or like you have to give it a type signature. So what is the result of this if expression going to be? There's a test value, so we check if this function is true, returns true, and if so, we return -1. Otherwise, we call some function. Okay. In Scheme, it's basically isomorphic to it, and in C, I had to do this with the question mark operator, which is cool. It's a cool operator, but always looks a little weird. And the next missing piece that we need to be able to do Scheme is we need some way of indirect function calls. So far, all the calls we've seen have been to a like specific function that you know well ahead of time, and that's really hard for Lambda. And so we still want like type safety and control flow integrity and all that. So in WebAssembly, you define a function table like I have in the top right over there. List a bunch of functions with their type signatures, and then you can have some code where you say, I want to call a function with a certain index. So in there, I'm calling index, say, 2, because that's what I've assigned to index previously. And then I look up in the table, and I check what the type is there. I see it matches what my call is expecting. And so then I can pass the argument to it, and then it runs. So we jump to that function. So that's how we can still get, we don't necessarily know the call site, but we still don't violate any of the safety properties that we want for WebAssembly. Okay, cool. So Bootstrapping Schism. Like, how did I get started on this? I want to talk about some design goals first. So I'll just go ahead and put all 4 of them up there. Simple, self-hosting, a subset of Scheme, and I wanted it to be standalone. So I wanted it to be simple because if you remember, one of the goals is I wanted to have kind of a playground where I could try out new proposals for modifications to WebAssembly, the spec itself. So that's easier if the compiler is simple. And if I can do it in, like, say, an afternoon rather than like 3 months to add a new feature or try it out, then that's a really big plus. Self-hosting, just because, like, I don't know, I feel like any self-respecting compiler should be self-hosting. I don't know, that's, it's just cool to have self-hosting compilers. And then a subset of Scheme, basically, originally I said strict subset here, and I was like, well, that means I can never finish it. Like, so it's, I want it to be Scheme, so any program that runs in Schism will run the same way in Scheme, or in another Scheme implementation. But it's not necessarily complete, but working towards that. And then standalone, this is sort of coupled with the simplicity. I didn't want you to have to pull in like dozens and dozens and dozens of dependencies. I wanted something that basically sat in a single file and had everything you needed to know. So, I kept this picture in my mind the whole time I was doing like bootstrapping this, which is that for every feature that I wanted to support in the language, there was like this trade-off that I had to make, which is how hard was it going to be for me to implement it, and how much was that going to pay off in the future? So, I didn't want to spend a lot of time implementing like really hard features unless they weren't going to benefit me also, and so I tried to strike a reasonable balance there. So the way I decided which features to support was I started out with a very simple, I wrote down this like super simple program. It just has a single function in it that returns a constant 5, and I wrote a compiler that could compile this. And so the first thing you do is you just have to, like, I started out by generating the simplest possible WebAssembly module, and that is it there, the bytes that would be in it. It's 8 bytes. It's I think that's a null terminated string that says ASM on it, although it's like the order's reversed on it. And then a version number, and that's basically it. And then from that point, I kept on adding more and more stuff. So there's a bunch of header sections you have to add to it, and so on. And then finally, I generated code. And so this is more or less what that program translated to. There is a module with a single function that returns a constant 5. Okay. So when this is all done, this is like half of the compiler. I couldn't get the font small enough to fit it on there. Please don't try and read that. But the important part is, like, there's 176 lines of code. I looked through there and thought, what features did I use in writing this? And I kind of knew I was doing this exercise anyway, so like, you'll notice there's no calls to Lambda. And well, you probably can't see, but there's no calls to Lambda in that first one. So what features did I decide to use? These are them. So there's top-level functions. So like basic control flow and comparison. So if and all that stuff. Variables, but mostly, for the most part, I just use the arguments passed to functions. Let binding came actually really, really late into the compiler, and which surprised me, actually. Quote and quasi-quote also surprised me, because I was like, well, you can just write cons and be done with it. But that got really tedious, and it turns out it's actually not all that hard to implement quote and quasi-quote. So I implemented it. The compiler got a lot more readable. It actually probably saved me lines of code, which was another goal I had, is to keep it small. We needed strings because we're reading. It includes a reader, so it's pulling string data off of the outside world and parsing it. And so then we needed a reader to parse it also. And the reader had to basically support all of the things that we had used before. So this led to some kind of interesting things, just like programming in this really tiny scheme. This is something like most compilers I've written have had all over the place, is mapping a function over a whole bunch of expressions. And I couldn't do that because I didn't have first-class procedure support in it. That wasn't on the list on the past slide. So I wrote a whole bunch of functions like this. Like there's probably a couple dozen of them in the original compiler that's just doing a loop and applying a function to it. And it kind of hurt every time I had to write that, but it was okay. Let binding, I mentioned this was really late, and this is why it was really late, because I realized you can just extract the body of a let out and as a top-level function just pass all the variables into it as parameters. And so this is sort of like even a poor man's let. So the normal like Lambda expression, but without even having closures. So yeah, and then backquote or like quasi-quote. This is something I actually did support, but anyway, that's you can do it with a whole bunch of cons. Okay. So the other part is I needed a runtime in JavaScript to actually connect it to the rest of the world. And you could write this runtime in other languages too, just JavaScript was most convenient because that's where our best supported WebAssembly embeddings are. And it only had 7 functions, and those are them. The add one function was just to make sure I could actually call JavaScript functions, and the rest of it is all like input and output, so it's super small. And then I also include a minimal interface so you can call from JavaScript to Scheme and not have to do a whole bunch of stuff manually. So to like load a Schism module and then run a function in it, it's a couple of lines of JavaScript basically to do that. Okay. So after I got it self-hosting, it's done, so ship it, right? So I did, released it on GitHub, and then it got on Reddit, and so they found me out. And like I agree, like what kind of scheme is this, right? So I added some more stuff to it. So better error handling, I'm not going to say much about it, but it does have Lambda now, so I guess it's a real scheme. And I added a really basic garbage collector. So Lambda, there was it's nothing super special there. You just sort of like lift all the functions out and build closures and do what you normally do when you implement a compiler for Scheme. Use call Indirect that I talked about earlier and so on. So that's Lambda. And it was about 300 more lines of code to add that. So the garbage collector, I'm going to take a little bit of a detour and talk about strings and symbols. So this is sort of why I needed it in the first place. So normally when you compare against a symbol, you expect to just be able to like compare a constant. You've made the string into a literal constant somewhere, and or not like the symbol into that, and so it's a really fast comparison. But that would involve making this table in static data, which I didn't want to do because I'm lazy. So instead, what I did is we expand it to everything turns into a string, and then I call the string the symbol. But then string would have had the same problem. So then we turn that into list arrow string. And then, wait, there's more. It turns into like, so when your whole compiler is a bunch of comparing against symbols like this, it allocates tons and tons of memory. So there's a line in there about how I basically ran out of 2 gigs of memory, and this is why. So I wrote a really simple garbage collector. It was like the first garbage collector I'd ever written, and it was like actually easier than I thought it would be. In JavaScript, it just like runs in between compiler passes. You explicitly pass it a root. It does a deep copy out of the old memory into a new memory. It is like just literally a semi-space collector, and then there we go. So future work, basically all the interesting stuff. So tail recursion, I have plans for how to do all this, but it's not supported yet, so we need to add that. The good thing is it is open source, so if anybody would like to help out, you can go there. I'm happy to review pull requests and help people if they want to contribute. So with that, I'll say thank you.
Thank you. Any questions?
This was awesome.
Thanks.
And I'm going to be a slight jerk and ask, so I'm really excited about the building scheme on top of WASM thing, but I'm also really excited about having our scheme stuff compiled to WASM, and my understanding is that the best path to that is the WASM garbage collection / manage object proposal. So I'm just curious if you think, since you're involved in the group, how likely that may become available to us schemers to be able to get our schemes compiling to WASM.
Yeah, so Andreas, actually, you should follow up with him afterwards because he probably knows this better than I do. But the garbage, like GC types, is like probably one of the biggest proposals that we're working on for it. I'd say because it's such a big change, it's still probably a ways off. But that's kind of, I see it as like kind of a race between when does, do I implement garbage collection in Schism before WebAssembly gets garbage collection natively? So yeah, I think if it's there, I would happily use it. But it's, I think, a ways off still.
Besides those buildings I/O primitives, do you have any special constructs so you can interact with other third-party JavaScript functions?
Not yet. It's I don't think it'd be too hard to add, but I haven't gotten to it yet. Cool.
First-class control question mark?
It's not there yet, but I think we can do it. Basically, you'd have to do a CPS transform of the whole program and all that. One of the proposals that's in flight is exception handling and maybe even a generalization of that to like full like delimited continuations, which I think will help, but I don't know that it's still going to be quite what Scheme needs. Scheme's call CC is like way more general than what most languages have.
So, Eric, you had these 4 S's.
Yeah.
Your design principles. Do you have any thoughts on what might have changed that might be possibly interesting and informative to WebAssembly if you, say, removed any one of them? Like, are there any that you thought about, like, oh, what if I did it without that one in retrospect?
Hmm.
Except for Scheme, that has to say.
What?
Scheme has to say.
Can
Yeah.
you repeat the question?
Oh, so the question was, I had my 4 S's for my design principles. How would it have influenced like WebAssembly if I removed any one of those? That's a really interesting question. I mean, I think the main thing was like being able to iterate quickly, and so keeping the compiler small and simple would have made that harder to do. I think getting rid of the standalone part of it or the simple part, I might have used LLVM as the backend. And that would have, I mean, realistically, that's what most languages targeting WebAssembly, I think, will do. So it might have added more feedback to LLVM and you know, like, I know like GHC compiles through LLVM now too, and so that might inform whether it works for GHC as well as C, you know.
All right, thank you. Any other questions, please take